in relation to the input and output voltages, and we said that those can be derived using the admittance parameters, which are your Y parameters. Similarly, the input and output voltages can be determined in terms of the input and output currents. And this relationship is shown by using the impedance parameters as indicated. And one of the last things we said last class was that the Z parameters were equal to the inverse of the Y parameters. And we will speak more to this closer to the end of this lecture when we look at some other things. So these are two sets of parameters that we have used to define our network, admittance and impedance. But there are two others that we are going to be focusing on this afternoon into evening. The first one being what we call the hybrid parameters. Now the term hybrid, whether we're dealing with a car, whether we're dealing with animals, hybrid simply means mixture. All right. So whereas for the admittance parameters, we were looking at the input currents in terms of the output voltages, and for the impedance, we were looking at the voltages in terms of the currents. For hybrid, we're going to be looking at a mixture of the input voltage and output current in terms of the input current and the output voltage. So that's where the mixture comes in. We are looking for a mixture of both input and output. That's a mixture. And secondly, we're looking at voltage and current. Again, another mixture. All right. So that's the hybrid parameters. The equations for these hybrid parameters are therefore shown. All right. So we have the input voltage being given by H11I1 plus H12V2, and I2 being equal to H21I1 plus H22V2. The other thing we need to take note of is the fact that with the admittance parameters, all the parameters were admittances. For the impedance parameters, all the parameters were also admittances. For the hybrid parameters, going back to the whole concept of mixture, these parameters deal with impedance, admittance, current, as well as voltage. Again, that gives us the idea of mixture. So we are looking at mixture in terms of the parameters we are looking at. We are looking at mixture in terms of the components themselves. All right. And we have gone through the exercise of naming these parameters. And we're going to use our knowledge from what we did in that for the admittance and impedance parameters and apply that to the hybrid parameters. So that's what we're going to be focusing on this afternoon, at least in the first part of the class this afternoon. Everybody have this? All right. So the matrix will be V1 and I2. And if we focus on that, if we focus on what we are finding, yes, then the rest of it will fall into place. So it's just V1 over I2 in the matrix. Everything else falls into place. So it's then I1 over V2. All right? Well, at least that's how I remember it. All right. So if we take the first equation, we're trying to find H11, then H11 is equal to V1 over I1. If you look back at the equation, yes, for the equation, if we want to find H11, then we make V2 0, and we're left with V1 over I1 with V2 0. All right. So we have done that already. So I'm just going to assume that you have revised that or revise that approach, and I'll take it from there. So H11 is V1 over I1. Now, based on the naming that we had done so far, what would be the name given to H11? Just by virtue of what you have learned so far, what is H11? Anybody? Or do I have to start calling names again?
Sir, I think it would be the short circuit input impedance.
Absolutely. All right. So H11, short circuit because it's a voltage made zero. Yes. Input because it's 1 over 1. And impedance because it is V over I. Excellent. All right. So H11, short circuit input impedance. All right. All right. So let's consider H12. Now, H12, we would have derived that from the first equation. So we're still with the first equation. We want H12, and for us to get H12, we're making I1 0. All right. So if I1 is 0, what kind of parameter is it? If a current is made 0, it is a
Short circuit.
Open circuit.
It's an open circuit. Excellent. So it's an open circuit because you're making a current 0. All right. So we know it's open circuit. All right. Now we have 1 over 2. So we have a mixture of input and output. So what would we call that?
Transfer.
Even though I'm going to modify that a bit. But fair enough, it would be transfer. And if you're dividing two voltages, if you're dividing an input by an output or an output by an input, what would you call it? Same quantity. What would that be?
Unitless, sir.
No, it will be unitless, but what would you call it? If I'm dividing output by input voltage, what would that
Voltage
represent?
gain, sir.
To be a gain. To be a gain. All right. But what we have here is input over output.
It'll be reverse gain.
It will be reverse gain because gain, as we would have expected, would have been output over input. Fair enough? Now, unlike the other parameters, and I am accepting the transfer, but just to distinguish it a bit, instead of saying transfer, what we are going to be saying is that it's a reverse. All right, so instead of transfer, we use the term reverse. So the full name for this parameter, yes, would be the reverse or open circuit reverse voltage gain. All right, and so we developed that name from 1. It's a voltage gain because it's a ratio of input and output voltages, yes. Because it's input to output, it's a reverse of that voltage gain, yes. And also, because we are finding it by making a current 0, it means that it is open circuit. So it's an open circuit reverse voltage gain. Are you comfortable with that? All right. Silence is an excellent thing at times. All right. So I assume everybody is comfortable. Okay. So we can take the other two parameters and apply the same principle in determining what these parameters will be. So H21 is V2 being 0. Yes. So if V2 is 0, it's short circuit. It is 2 over 1. Yes. Well, before I deal with the 2 and 1, yes, it's I over I. So again, it's a gain. Everybody agree with that?
Yes, sir.
Yes, sir. Yes, sir.
Now, by extension to the one that we just did, which was H12, we said reverse voltage gain. So, just to be good engineers, we're just going to be trying to be consistent. try to be consistent. So if 1, 2 is reverse, then 2, 1, we're going to call it forward. All right? So H21 would be the short circuit forward current gain. All right? And then finally, H22. Come on, somebody give me the exact name for this, the precise name for this one.
Open circuit.
Open circuit output admittance.
Okay, good. Open circuit output admittance. Excellent. So remember I was talking about the mixture? Here are the 4 parameters described. We have impedance, which is H11. We have admittance, which is H22. We have forward current gain, yes, which is H21. And we have reverse voltage gain. And so you have it all mixed up, eh? And as I said, the hybrid means mixture. So it's a mix of parameters, okay? And so these are our H parameters. So you have H, we have H11, H12, H21, and H22. So those are our hybrid parameters. Okay. All right. So as before, we go to our trusty network. All right, same network we had before. And there's a reason I'm continuing to find the parameters for this network. All right, all will be revealed. All right, so for this network, I'm gonna start by finding H12 and H21. And in both instances, I'm doing that because in both instances, I will have to short circuit port 2. All right. So if I short circuit port 2, right, so if I put that short circuit there, then it means that V2 is 0. And the first parameter we want to find is H11. So H11, based on the definition we had just now, H11 is equal to V1 over I1, and that is with V2 being equal to 0. Now to do that, if I'm looking into the V1 port or into the input port, I'm looking in here. The relationship between V1 and I1 with just the impedance looking in. Yes? Now, because I have the short circuit at port 2, it means that all we have is the 5 and the 10 ohm resistors in parallel. All right? So we can solve that. We get V1 over I1 to be equal to 10 over 3. Okay? All right, so V1 over I1 or H11 is 10 over 3 ohms. So we can now move to H21. And I'm doing H21, as I said before, because it will also be found by making V2 0. So since I already have the short circuit, I'm just going to find H21, although it's from equation 2. Okay? Everybody has this? All right. Now, with the short circuit still in place, H21 is I2 over I1. So we look back at the circuit. What I'm trying to determine is a relationship between I2 and I1. And based on what we have here, I2 would be the current flowing through this resistor. Current flowing through the 10 ohm resistor. Agreed? Now, if that is I2, if you look at I1, if I should divide I1 between the 5 ohm and the 10 ohm, then there would be a component of I1 that is flowing through the 10 ohm resistor. So I just use current division between the 5 and the 10 ohm resistors in order to find what component of I1 is going through the 10 ohm, which of course would be equal to the negative of I2. Since we all agree that only one current is flowing through the resistor, yes? So by that token, minus I2, and this is the current division for I1, yes? So 5 over 15, 5I1 over 15 is equal to minus I2. What we are interested in is I2 over I1. So I2 over I1 would be equal to minus 1 over 3. All right, so we have H11, we have H21. So I can now move to finding H12. All right, and H12 will be found by making I1 0. All right, so for I1 to be 0, it means that this port is open. All right, so if it's open, it means that I1 is equal to 0. But of course, bear in mind, we still have a V1 there. Eh? We still have voltage across the 5 ohm resistor, which is V1. So I am interested in finding H12. So H12 would be V1 over V2 with I1 0, or port 1 open circuited. All right. So we look at this again. All we're trying to do, students, is to find the relationship between V1 and V2. Just find a relationship that connects the two. And based on what we have here, if port 1 is open, then V2 will be seen across the 20 ohm. Yes? And all we'll be calculating would be, or all we'll be doing is dividing V2 between the 5 and the 10 ohm resistors. And if I do that, we're doing current division, it will be 5V2 over 15. So 5V2 over 15 is equal to V1. What we are interested in is V1 over V2. So that gives me 1/3, and that would be H12. Am I going too fast? Is everybody following?
I'd like to go back, sir.
I didn't get that.
So I said I would like for you to go over about this section, sir.
Oh, okay. All right. If you look back, H12 is from equation 1. All right. So equation 1 says V1 is equal to H11 I1 plus H12 V2. Okay. So in order to make, or in order to determine H12, we'll make I1 0. I1 being equal to 0, what we are saying is that this port 1, is open circuited. All right. So I need now, based on the network as shown, I need to determine the relationship between V1 and V2. V1 would be the voltage across the 5 ohm resistor. Agreed? V2 would be the voltage between those 2 points. All I am doing is using voltage divider to write or to determine the voltage across the 5 ohm resistor in terms of V2. So that will be 5V2 over 15. But we know, as I said earlier, we know that V1 is also the voltage across the 5 ohm. So we get this expression. So V1 is equal to 5V2 over 10 plus 5.
Okay.
We rearrange this expression for V1 over V2, and that is equal to a third, which we know since V1 over V2, as shown up here, is equal to H12. All right. Okay. Since we, again, with I1 0, we can also find H22. And H22, we'd be looking into this port, and H22 we know is equal to, it's an admittance, so it would be I2 over V2. So if I simply find the impedance looking into port 2 and then find the reciprocal, I would be able to find H22. All right? So H22, yes, and the 20 in parallel with 15, because we have the 20, and then of course the 10 and the 5 would be in series. Remember, that's equal to 0. All right? So V2 over I2 is 300 over 35, or H22, which is I2 over V2, which is a reciprocal, is equal to 35 over 300. If you want to simplify it, be my guest. But because I have a couple of things up my sleeve, I'm going to leave it as 35 over 300. So the H parameters, the hybrid parameters for the network would be that. All right. So we have these hybrid parameters. And again, I'm just going to go back to what we did earlier. So I'm going to go back to the network that we looked at last week. From that network, find some of the unknowns. So here's my network. And here's the question. For the network shown below, use the hybrid parameters to determine the power dissipated in the 4 ohm resistor. And once again, students, as you can see, we can take out this network and we have the H parameters for this network. Right? The H parameters being 10/3, 1/3, minus 1/3, and 35/300. All right, so those are our parameters. Now, everybody will approach a problem, their own unique way. But until you have worked out your best approach, I'm going to suggest that the first thing you want to do when you are doing these questions is just to write back the initial equation. All right, so rewrite back the original equation. So here we have the original equation: V1 equal H11 I1 plus H12 V2, I2 equal H21 I1 plus H22 V2. We had already written expressions that linked I1, V1, the 10 ohm resistor, and the 15 amp source. We have already established that. We have also established the relationship between V2, I2, and the 4 ohm resistor. So our objective now is to make the substitutions in these equations that we have before us. All right, so we want to make the substitution so that we are left with only 2 unknowns, because only 2 equations we have. And that will always be our objective. So let's make the substitution. Let's start with equation 1. All right. Now, remember, we had derived an expression for I1. Where's my pen? I1, we said was 15 minus V1 over 10. All right? That's what we had for I1. And for V2, we had that V2 was equal to minus 4 I2. All right? So we had those from last week. So all I'm going to do is to substitute for V2 and I1. So I1 and V2, I'm just going to substitute for these in the next slide. So that's I1, that's V2. And for the second equation, that's I1, that's V2. All right, so I've substituted for I1 and V2. There's also a next set of substitution that I have to make, because remember, we have the values of H11, 1, 2, 2, 1, and 2, 2. So I'll make those substitutions now. So in making those substitutions, I end up with that. All right. What have this? Just a minute, sir.
1 minute, sir. Ready when you are, sir.
Okay. All right, so continue the simplification. All right. So our equation simplify to these two. Okay. And as I am sure you were expecting, the final answers would be as before. If we solve these two equations, we'll get V1 to be 40 volts and I2 to be minus 2.5. And we made the other substitutions for V2 and I1, and we'll get that. Okay? So I'm going through all of this with the same circuit just to highlight the fact that I can use any set of parameters to describe the circuit. And in using these parameters, I get the same result. All right? Nothing will change. Now, please verify that these values are correct. So just punch in the values for me and make sure that they are correct. All right, now, couple of things, and just to bring some utility to what we just went through this since this afternoon. The hybrid parameters are things that you'll be using, or in some instances, some of you would have already used based on your advanced status within the school. But these are parameters that you're going to encounter. So let me just try and provide a brief introduction. Okay. Now, if you go back to the naming, all right, we had H11, so we had H11, and we said that that was the input. We said that was the input impedance, right? So H11 was the input impedance. We had that H12 yes, that was our reverse voltage gain. Yeah. H21 was our forward current gain. And H22 was our output admittance. All right. Now, what we're going to focus on are just the the first words that I have in these descriptions. So for this input, I'm going to focus on just the I. That's a clumsy way of putting it, but anyway. So we're going to focus on just the I part. For reverse, we have R. For forward, F. And for output, we have O. Now, in your electronics class, you would have talked about transistor biasing. Now, in terms of how you connect your transistor, your BJT, you have that one of the three terminals would be common to both the input and the output circuit. And the one that is common to both, then you say that that's how you're biasing the transistor. Fair enough? So the common one that we're most familiar with would be emitter biasing, right? So for the H11, using the I, I'm going to use the E, right, to show that I'm dealing with the emitter. Now, H11, taking the I would have HIE. Yes? For H12, it will be HRE. For H21, it will be HFE. And for H22, it will be HOE. So we'll have the input impedance, that's your HIE. You'll have the reverse voltage gain, which is HRE. You'll have the forward current gain, which is HFE. And HOE would be the output admittance. And these, ladies and gentlemen, would be the hybrid parameters for your BJT. Comes under the topic that you would have done known as small signal analysis. Yes? And so typically what you would then be exposed to is what we refer to as the or the pi model, sorry, of your transistor. And so we would be able to know, have that model, yes. So this becomes, or this is your two-port network. Right? So that's your two-port network, that's a transistor. And what you connect on the other side, of course, this is a common emitter, right? So that's common to both the input and output side of your circuit. Yes, that would be a collector and that would be a base. So what you connect on either side, whether you're depending on the type of biasing that you're using, whether you're going to be used, but not biasing, whether you're direct coupling. So if you're going to just feed this output into another input, you're putting a two-port network into another one. How you connect it, that's something that we'll discuss next week. But I'm just putting this out there so that you appreciate that what we're dealing with two-port networks has application. As we said before, at the start of this topic, has application in electronics. The next one that we will look at, which will be the transmission parameters, they will have application to your power engineering. All right. So, having dealt with this, we now move to the transmission parameters. So let's quickly summarize what we have done so far. You have your admittance parameters that gives you the input and output currents in terms of the input and output voltages. You have your impedance parameters, which gives you the input and output voltages in terms of your input and output currents. You have your hybrid parameters, the mixture, which gives you your input voltage and your output current in terms of your input current and your output voltage. For the transmission parameters, what you have, well, they are designated by A, B, C, D. What you have is a relationship that gives you the input voltage and current with respect to the output voltage and current. All right? Now, note the major difference between these equations. For your transmission parameters, there's a minus sign here. All the other equations, we had a plus sign. The reason why you have the minus is because you're dealing a transmission, it is expected that the current on the output side would have been flowing out of the network. So it would be I2 would be going in the opposite direction. But because we are using the convention that I2 is coming into the network, then the parameters or the equations, for the equations, we have the minus. All right, so in matrix form, all right, again, please take note, we're dealing with minus I2. That's where a lot of students run into problems with these parameters. All right? So hybrid.
You can explain why it's minus again, please. Up top.
Because I'm saying for transmission, right, you're transmitting. So if you're transmitting, it means that the output must be heading out of the network. The convention is that I2 flows into the network. That's the convention for two-port networks. But for a transmission, if you're transmitting, it means that the signal would always be leaving the network. So what we have is minus I2.
Yes, sir. I see it now. I see it.
Okay. All right. So with this, and because we are no experts, I just give you all the equations. All right. So A will be V1 over V2, with I2 being equal to 0. B, V1 over minus I2. So it's V1 over the negative of I2, okay, with V2 equals 0. C, I1 over V2, I2 equals 0. And D, I1 over I2 minus I2 with V2 equal 0. Nomenclature, is that sure? I just did this for me. I'm going to.
Sir, I don't like what you assume, so we're expert in it, sir.
It's not an assumption, I know. I know you're experts. 2 weeks of doing the same thing? Oh man, come on. Just give me a second. Okay, sorry about that. All right, so as you would have expected, we go back to our trusty little circuit. And again, we want to find in this instance, we want to find the transmission parameters. So with V2 made, well, rather I2 made 0. And so we're looking at the if I2 is made 0, then we're finding A and C. All right. So A is V1 over V2. All right. So A is V1 over V2. Now, what will be the voltage across the 20 ohm resistor? What's the voltage across the 20 ohm resistor? Got it? V2. All right. Now, what is the voltage across the 20 ohm resistor with respect to V1? So if you're taking it now from port 1, what will be the voltage across the 20 ohm resistor?
0.
Look, you're at port 1. What's the voltage at port 1?
20 V.
No, what's the voltage? What's the voltage at V1 at port 1?
That'll be V1.
V1. So if the voltage at port 1 is V1, what's the voltage across the 20 ohm resistor with respect to V1?
20 V1 over
V2.
10 V1 over.
Would you use voltage divider rule?
We're using voltage divider. Which two resistors are in series?
5
10
and
20.
5.
10 and 20. Yes. All right. So the 10 and the 20 would be in series.
Mhm.
Right? So if the 10 and the 20 are in series, what's the voltage across the 20 ohm?
So it's 20 V1 over 30.
Thank you. All right. So 20 V1 over 30, looking at it from this end. Yes. And we know that the voltage across the 20 is also equal to V2. So V2 is 20 V1 over 30. But what we are interested in, this is where you now need to be careful. What we are interested in is V1 over V2. All right? We're interested in 1 over 2. So I now need to rearrange to get 1 over 2. So 1 over 2 would be 30 over 20, or 3 over 2. So A is 1.5, or 3 over 2. Okay? All right. So we can also find C. Yes, and we know that C is I1 over V2 with I2 equals 0. So maintaining the open circuit, you have the circuit before you. based on I1, yes, how would you determine the voltage across the 20 ohm resistor? First of all, what would you need to calculate?
Sir, can you repeat that question?
Based on I1, I1 is the current at port 1. Let's go back at the diagram you have in front of you. Yeah? I1 is going into the network. Based on that current, what will be the voltage across the 20 ohm resistor?
Sir, 5I1 over 10 plus 20.
Look again. You're missing something. What will be the current through the 20 ohm? Let's start there. Remember, port 2 is open circuited, yes? So I2 is 0. I1 is now coming into the network. What would be the current through the 20 ohm resistor?
Over 20.
Let's say, would it be 5 over 30 minus I1?
No, sir, no minus. We're dealing with I1. All I'm looking at is I1, you know, I1 flowing in.
30 times I1, sir.
Go again?
5 over 30.
Times.
Oh, you get 30.
35.
35, yeah.
35.
Yes, sir.
Oh, yes, for true. Yes, sir.
So it's 5 I1 over 35. So that's the current through the 20 ohm. Agreed? Everybody agree with that?
Yes, sir.
All right. So if that is the current through the resistor, that's the current through the resistor, what would be the voltage across that resistor?
V2.
Huh?
Through the V2.
No, listen carefully to the question. If the current through the resistor is 5 I1 over 35, what is the voltage across the resistor?
Sir, 20 times that.
20 times that, which gives us 100 over 35, right? 5 I1 over 35 times 20 gives us 100 I1 over 35.
Yes, sir.
Yes, sir.
Yeah? And that is also equal to V2. Because V2 is the voltage across the 20, isn't it? Remember, ladies and gentlemen, the objective in finding these parameters is to find a relationship between the two variables. So C is connecting I1 and V2. Your task is therefore to say, okay, how are I1 and V2 connected? And based on what you have before you, I1 would divide between the 5 and the 30 ohm resistance. So the current going to the 30 ohm resistance would be 5 I1 over 35. That would be the current through the 20 ohm resistor. Therefore, the voltage across it would be 100 I1 over 35, which is also equal to V2. So you rearrange that for C, right? You get C equal to 35 over 100. All right. So we just operated, or we just found A and C by open circuiting the output port. So we can now find B and D by short circuiting that port, or in other words, making V2 0. So let's find B and D. So if I short circuit the port, what I want is B, which is V1 over minus I2. Right? This is two resistor circuit analysis. Right? If V2, if the port 2 is short circuited, how much current will go through the 20 ohm resistor?
0.
Exactly. Nothing will flow through it. So which resistor would I2 be flowing through?
10 ohm.
10 ohm. Now if that is I2, yes? If I2 would be flowing, in what, by the way, in what direction would I2 be flowing through the 10 ohm resistor?
Opposite direction of I1, sir.
Huh?
Opposite direction of I1. Negative direction.
So I2 will be flowing right to left.
Yes, sir.
Okay. So I2 going right to left through the 10 ohm. However, what is B equal to?
V1 over minus I2.
Okay. So minus I2 will be going left to right. Agreed?
Yes, sir.
Yes,
If that is the case, what is the relationship based on the circuit before you? What is the relationship between V1 and I2 minus I2? What connects them?
So 5 ohm.
I'm listening. You finish?
Wait, sir.
You all agreed. We are all agreed that no current will flow through the 20 ohm, right?
Yes, sir.
Yes, sir.
All right. Now, if no current is flowing through the 20 ohm, how are resistors 5 and 10 connected with respect to V1?
In parallel.
In parallel. So if they're in parallel, what is I negative I2 with respect to V1?
Sir, V1 over 10.
V1 over 10. That's it. Come, gentlemen and ladies, don't make this thing more difficult than it appears to be. Right? So V1 is equal to minus 10 I2, which means that V1 over minus I2 is 10. So B is 10. All right. And for D, yes, for D, it's I1 over I2. So again, let me go back to the circuit. That's I1, that's I2. Based on the flow of I1, what's going to happen to it between, as far as resistors 5 and 10 are concerned?
It is gonna share.
Divide.
They're going to divide between the two. Okay? And how will it divide? What component will go through the 10 ohm?
I2.
Hmm?
I2.
Oh man, you guys not listening. Listen to what I said. You just said I1 would be shared between the 5 and the 10. So I'm asking what component of I1 will go through the 10 ohm? It can't be I2. What
Sure.
component of
5
I1?
I1 over 15.
Thank you. 5I1 over 15. All right? That's the component that will go through the 10 ohm. But that component is equal to
So negative I2.
minus I2. They're getting the hang of it now. So 5I1 over 15 is equal to minus I2. Okay? Which means that I1 over minus I2 is 15 over 5, which is equal to 3. So D is equal to 3. So we can write the matrix, the transmission matrix. And for this one, it's capital T. Right? So we have D as 3. We had B as 10. We had C as 35 over 100. And we had A as 3 over 2. So those are my transmission parameters. All right. So what I wanted to do is to go back to our trusty little circuit. I didn't put the solution here. Go back to our trusty little circuit. And we're going to repeat the question. All right. So here's the circuit I'm referring to. All right. We're going to repeat the question using the transmission parameters. All right. So let's put transmission. All right. So the transmission parameters. So you know that V1, I1, is equal to T into V2 minus I2. All right. So let's repeat that question for me. I will give you, it's now 6:09. I give you 10 minutes to complete that, and then I'll come back to you and we will wrap up this section of two-port networks by looking at the relationship between these sets of parameters that we have developed so far. So it's now 6:09, call it 6:10, and I'll come back to you at 20 minutes past 6. In the meantime, I will just take the register. All right, this is the last time I'm going to say it. The next time I come on and I am seeing whether ID numbers or names I don't recognize, I'm just going to mark you as absent. So whoever is 1605-103, I have no idea who you are. And so since I'm not getting any feedback on that, I will just assume that you wish to be absent. Okay, so we're back. Whoa, whoa, whoa. All right. So is anyone able to confirm any other values? Nobody?
Yes, sir.
Yes, sir.
Yes, sir. I got it. I feel accomplished, you know.
Excellent. Excellent. Success breeds success. That's excellent. I'm happy to hear that. Very happy to hear that. Now, if you go to your Schoology page, I'm trying to remember where it is located. I believe it's in it's in lecture notes. Yes. If you go into lecture notes, you'll see parameter conversion matrix. All right. Now that document is what we have displayed on the screen. All right. So it's this matrix that you will see. Now, what I'm going to do is just spend a little time explaining how you go about using this matrix. All right. So of course you can see that it's a matrix consisting of matrices. All right. And the question is, how do I and why would we need this? Now, based on all we have done since last Monday, in terms of looking at the admittance, impedance parameters, and today we looked at hybrid and transmission, you will agree with me that maybe admittance parameters, it was easier to derive those parameters as against the transmission or against the hybrid. Whereas the hybrid, was a mixture of different parameters: voltage gain, current gain, admittance, and impedance. And similarly, the transmission parameters. So it may be easier, depending on the network you have before you, to find one set of parameters over another. And this matrix that you see before you gives you the opportunity to find a set of parameters and convert them into another set. So let us say you are comfortable finding the impedance parameters. So what you have are the Z parameters, okay? And let us say what you wanted were the hybrid parameters, okay? So you have Z, so have, and you want H. Now to go from Z to H, listen carefully. What you have, you move in the vertical plane. So you move vertically with what you have. What you want, you move horizontally. Where they intersect, that's the matrix that you're going to use. I'll do that again. You have your impedance parameters because, with practice, you are better able, or you're much more efficient at finding these parameters. So you have impedance and you want transmission. So you want transmission, which is right here, and you have impedance, which is right there. Okay? What you have, you move vertically. What you want, you move horizontally. Sorry. And where they intersect, that's the matrix you're interested in. So if I'm going to convert my impedance parameters to my transmission parameters, then I will use this matrix. Okay? Now write down that matrix for me, since I didn't give you any notice, so you wouldn't have had the sheet before you. So let's write down this matrix for me, please. Z11 over Z21, delta Z over Z21, 1 over Z21, and Z22 over Z21. What do you have that?
Yes, sir.
All right. So we're now going to, I'm just going to put back the four set of parameters that we have already developed. All right. So these are the parameters we have. And these are our impedance parameters. Okay. So it says that the transmission parameters would be Z11 over Z21. So Z11 would be 100 over 35. What's that? Is that correct though? It's supposed to be 150, right? So it's 150, wasn't it? Let's double check that for me. How much?
Sir, it's 150.
It's 150.
Yes, sir, for Z11.
Yes. All right. So this should be 150. Thank you. All right. Good. So we have 150. Over 35. And we are dividing that by Z21. And Z21 is 100 over 35. So we'll be multiplying this by 35 over 100. All right? And that would be our corresponding A. Good? So 35 will cancel, and so we get A to be 150 over 100, which is 1.5. Everybody good with that one?
Yes, sir.
Is there anybody who did not follow what I just did? Did not understand? See what I just did? I'm just making the substitutions. Nothing fancy. So I'm going to jump to C. So C is equal to 1 over Z21. Good? Z21 is 100 over 35. So C is 35 over 100. Okay? For D, from the matrix that you just did, is Z22 over Z21. Z22 is 300 over 35. So that is 300 over 35. 35 times 35 over 100, and that's equal to 3. All right? And so far, you agree that we are spot on. So you have the 1.5, and that is 3 over 2. We have 35 over 100, that is C. And of course, 3, that is D. For the for B, however, what we have is delta Z, which is simply the determinant of the Z matrix. Everybody following what we have done so far? Because I'm going to erase what I have on the slide.
Yes, sir.
All right, cool. Let me just remove all the ink. Remember that this is 150, all right? Okay, so delta Z would therefore be 150 over 35 times 300 over 35 okay, minus 100 squared over 35 squared. All right. 150 times 300, so that would be 45,000. So we get 45,000 over 35 squared minus 10,000 over 35 squared. So that gives us 35,000 over 35 squared. All right?
28.57.
No, man, it's not every day we want decimals, you know. You have to work with my fractions. Fractions are beautiful creatures. All right? So we take out the 35, and this gives us 1,000 over 35. All right? Everybody agree with that? We get 1,000 over 35. That is now delta Z. And B is equal to delta Z over Z21. So we have here 1,000 over 35 times 35 over 100. All right, so we get 1,000 over 100 equal 10. All right, no need for a calculator. And of course, that is what we have here. So I've just used the matrix to convert from impedance to transmission parameters. And we can do that for any set of parameters. Any question? Would you like us to do another one? All right. So I agree with you. So let us convert from Y to H. All right. Let's convert from Y to H. And please remember, this is 150, all right? 150. No, I'm not going to use it again, but anyway. So I go back to my matrix. All right. What is it that I have? What am I converting from?
From Y, sir.
From Y. So in what direction do I go?
Vertical.
Vertical. So I'm in this plane. What do I want?
H.
So I go horizontal. So this is the matrix we're going to use. So you can just write down that matrix. All right. So our matrix is 1 over y11 minus y1 2 over 1 1, y2 1 over 1 1, and delta y over 1. We all have the matrix?
Yes, sir.
All right. Now that we have the matrix, here's my admittance matrix. Sorry, I put it in so we can put it back. So y, if it makes it easier for you, 3 over 10 minus 1 over 10 minus 1 over 10 and 15 over 100. All right? Should make the conversion a lot easier. So you're converting from y to h. So just do that for me quickly. Yeah, you don't need more than 5 minutes for that. Mr. Wilson, nice of you to join us.
Yes, sir. I was at work. I just got a chance. I was on a call. Sir, sir, this video will be posted.
Mr. Wilson, man, do the problem, man.
I'm just trying to look for
Mr. Wilson, you're disturbing us. Thank you, sir. All right, students. All right. Anybody have a difficulty converting?
No, sir.
No, sir.
Excellent.
Sir.
Excellent. More accomplishment, Mr. John, Mr. Adams.
Yes, sir.
Excellent. All right. So this is where we're going to pull stones up today. I just think I don't think it's necessary for me to say that you know, this new environment, you can be lulled into a false sense that we are not doing a lot of work, but you have covered quite a bit in the last 3 weeks, right? And as usual, I'm not gonna stand over here with a big stick telling you to practice, but it is absolutely important that you know, in your own time, you try some of these questions and make sure you understand the concepts. And I'm saying this because on Wednesday we'll try to have a tutorial session on two-port network so far. You know, there's some basic applications before we move to the final stage of two ports. And it is going to be important that you understand the fundamentals for Wednesday to be of any benefit to you. So if you don't spend time going back through the last 3 sets of lectures, reviewing your notes, practicing, then, you know, we'll be wasting time come Wednesday. And you know how I feel about wasting time. So I'm going to end it here for today. Have a productive evening.
Sir, I have a question, sir.
Yes, Mr. McFarlane.
I was stuck in a rock hard place, sir, in terms of wondering if I should use the conjugate of the current to find the power in network, like the power dissipation. No, not the power dissipation, the power supply by the source.
Oh, who put you in that hard place, Mr. McFarlane?
When I look at the solution, I realized that my answer was off.
Well, Mr. McFarlane, it is always the case that you are using the conjugate of the current to find the supplied current by the sources.
Oh, okay.
It's always the case.
All right, sir.
All right?
Yes, sir.
Yeah, man. Cool. Yes, Mr. Nevers.
Yes, sir. Evening. You're gonna be available anytime before Wednesday for questioning consultation.
Send your questions. I'll answer them.
All right, sir. Respect.
All right, the discussion forum will be open in Schoology. So that's where you'll add your questions so everybody can benefit from the responses.
All right, sir.
All right. All right. There be no further questions. Have a good evening. All the best. Take care.
Yes, sir. Indeed, sir.
Cheers. Good.